keep putting this up on the board every lecture. I'm going to do that. If it starts to become annoying, then that means that you get what's going on and you're used to this now. So that's great. So let's aim for it becoming annoying. So yesterday, we talked all about binomial data. So we did this whole work process for data of that kind of distribution. And today we're going to work through some examples on that. So we started off with data that was binomial from where we observe some X number of successes out of n trials where we could just have a success or a failure in each of those n trials. And we want to learn about this parameter theta that describes the probability of a success. And I told you that the conjugate distribution for our prior in this case is a beta distribution. And then we did this whole prior to posterior analysis where we worked out that this posterior then is that we take this beta distribution and we add the number of successes that we've seen to our prior A, and we add the number of failures that we've seen to our prior B. And then we looked at some moments from that. So the example that we're going to do is this GM sheep example. And in this case, this GM company have taken 30 sheep. So we had n trials, and they were looking at what the number of sheep that are resistant to some disease are. So our successors are being resistant. And they observed 18 of those, and that was binomial. So the first thing that we're going to look at is a prior set by the GM company itself. So this GM scientist said that they believed that theta was equal to 0.95. Let's check that. Yep. So they thought and they are almost certain that theta is greater than 0.8. So if we were going to fit a prior distribution to this, how do we go about doing that? We have information on maybe some sort of expectation, if their sort of most likely choice for theta was 0.95, but we don't have this variance. We have this sort of ambiguous statement about some sort of cumulative distribution. So if we were to put this into some sort of notation that they believe this probability to basically be 1, then we can look in R to how to choose an A and a B based on that. So this was basically trial and error based on what this is going to equal. I'm guessing Miguel just chose a few values to actually try. There is some sort of, there's an R function online that lets you do some sort of prior elicitation with beta distributions that you can play about with. But if we were to choose an A equal to 19 and a B of 1, then this prior expectation from a beta distribution is equal to this statement that the scientist has said. You could choose a whole host of A and B that would lead to the same expectation, but in this case, if we look at this interval, We can get this kind of probability just from R. So if you use the p beta function, so we can just do that, actually. So if we did p beta of 0.8 with these parameters of a and b that are 19 and 1, we get this probability, and 1 minus it is 0.98. So this probability that theta is greater than 0.8 is basically 1, because it's 0.9, with that value of a and b. Getting an a and b that matches up both this expectation and this quantile is kind of guesswork in this case. If you were to have some sort of coursework in this, maybe you'll be expected to do a work through like that, where you need to use something like R to work out these quantiles. In a sort of exam case, you're not going to be able to do that because you don't have R. So it's probably going to be some sort of expectation and variance that you're given, and then you can work out A and B from that. There'll be examples in your exercises booklet on doing that. There'll probably be examples of both kinds of cases. So that gives us this prior for the GM scientist, and we can get our posterior distribution from what we worked out yesterday, in that we have this posterior here where we add our successes to A and add our failures to B. So the GM scientist's posterior then is this beta distribution, and we've already done all the hard work yesterday doing this. This is now just a case of plugging in some numbers into what we've already done. So we have and that posterior distribution then isn't that helpful to us, because if we were to go back to the GM company, or if we were to, they were to release some sort of news statement based on how good their new resistant sheep are, then the general public aren't going to know what this beta distribution are, but they might know things like means. So, or if we give them some sort of interval that we expect the proportion of sheep to be in, they can relate to what that means. So we might want to look at some posterior derivatives, and if we look at the posterior expectation, then we know that from a beta distribution, and we get 0.74, and we can look at the posterior variance, so we've gone from a prior expectation that the GM scientist had, that their expectation of theta was 0.95, and they had this sort of great certainty that it was going to be greater than 0.8. In reality, the observations that they saw, that they had 18 successes out of 30, their sort of maximum likelihood estimator from the data would be 0.6. So they expected theta to be really high, 0.95. They saw in their experiment that some sort of maximum likelihood estimator of theta was 0.6, and they've ended up with this posterior estimate of 0.74. And the prior variance, because the GM scientist was so certain about their beliefs of theta, so their prior variance was so small, this posterior variance is really small as well. So we've got this tight distribution around this, and I believe that we have a picture in R to show us this. That's as nice as we're going to get it. So we can see that theta can only take values on 0 to 1. The prior that they had is this red line. That's really, really tight around the high values of theta. The observations that we've seen, this x equals 18 out of 30, gives us this purple likelihood that's centered around this maximum likelihood estimator of 0.6. And then our posterior is somewhere in between those. So if you were the general public and the GM company had done this trial, they'd done this analysis, and they'd come out with this posterior expectation of 0.74, and they went to a bunch of newspapers and said, look how great our GM sheep are. We have this resistance of 0.74 to this disease. What does that make you feel about Bayesian statistics? They only had a trial that had 0.6 proportion of their sheep, but they're now saying in the news that they have a 0.74. So when we don't get the information on the prior that people have used, the whole idea of Bayesian statistics becomes a little bit ridiculous. We need that information on what our prior was, because that's subjective and your prior might be different from my prior, and this posterior is wholly based on that. We need information about that prior to make any judgments on whether or not we actually believe what this posterior is. And so somebody that might not believe that is a Greenpeace activist, I think is in the notes. Yep. So they've come and they've seen the results of the trial that they were 0.6, and they've said, why on earth are the company now quoting this 0.74? And then they looked at this prior that was set by the GM company, and it was so high they believed that theta was 0.95, and they said, I don't believe that. I would never have put that kind of certainty on what theta is. So they might want to do the analysis themselves with their own prior. So the activist doesn't like GM sheep, and they think that it's going to be a really low probability that this modification is going to have made any difference. So they're going to believe that theta is small. So the proportion that the sheep are susceptible is small. So they might give a prior of 1 in 19. So we're just switching those parameters around now. And that leads to a really different kind of prior on theta. So our prior expectation then and their prior variance. Oh, we didn't look at the variance. We were looking at this probability of being greater than 0.8. So again, you can put that into R, and you get something that's really, really small. So in contrast to the GM company, this activist thinks that theta, the proportion of resistant sheep, is really low. It's almost at 0. But just like the GM company were really certain about what they thought theta was, they're still really certain about what they think theta is. So this probability that it could be over 8 is basically 0. So we've got almost the exact opposite in terms of what this activist believes to what the GM company do. And if we work out their posterior by, again, we're just plugging these numbers into the formulas that we got yesterday. We get our posterior distribution, and again we can compare these moments of our posterior with the moments that we worked out for our GM company. So the activist, their prior was that theta was really, really small. Once we've had this data that indicated that theta, our maximum likelihood estimate, in any case was 0.6, then their posterior expectation goes to 0.38. So it increases, but because they were so sure about their prior, it had this really small variance. They basically had no belief that theta could even be over 0.8. Their posterior then is still quite tight because they were quite certain before, so their posterior is quite certain. So we still have, it's bigger than it was before because our data have brought it up, but this probability that it's over 0.8 is still basically pretty much 0. So we can compare that with our GM scientist, and we get that the prior for the activist was basically the exact opposite. Our likelihood is still the same because we're still using the same data. That curve's exactly the same, but then our posterior then is somewhere in between. So we get these two really different posteriors here. And in terms of anybody believing some sort of analysis on Bayesian statistics, it's quite hard to see that we can do some analysis based on this because we're getting such different results. It's depending so much on these priors, and these priors are just based on whatever that person that's doing the analysis has believed about data. And we can see that you can get people that can have completely contrasting views. But it's not that ridiculous because all of this is really hinging on how much data we have. So in this case, we only had n equals 30. If you were to have some sort of clinical trial with 30 participants, that wouldn't be a clinical trial. So if we were to increase our data, we already looked yesterday at, when we looked at our posterior moments from this, that as n increases, all of these moments tend towards things that are based on our maximum likelihood estimator. So if we were to instead get more data, so we had, instead of n equals 30, we instead had 1,000, we had 1,000 trials, and then we observed 610 of those, 1,000 sheep to be resistant. Then our posterior changes because we still have our same priors for our GM company and our activist, but our posterior is based on this n and x, and we end up with, you can put these numbers in yourself. So now, the GM scientists that believed that theta was around 0.95, their posterior expectation's gone to 0.617, so that's pretty close to our maximum likelihood estimate. And our activists that thought that theta was really small, they thought theta was around 0.05. This goes 0.599. So these things aren't exactly the same as one another, but this increase in data has made them really, really close compared to what they were before, when they were completely different kinds of posterior estimates. This shows what happens in that case. So we still have the same prior distributions, our red lines, but now we have more data. So as we get more data, our estimates, our n gets bigger, and all of these things like our posterior variance get smaller. So these distributions are a lot more peaked and narrower, and they're more close to one another. So do we have I think we have another plot. Okay, so this just shows the posteriors and the likelihood. So we've still got our likelihood in purple, and then we have our two posteriors for the activist and the company. They're not the same, but they're similar, and they're similar to our data now, whereas before they were being pulled towards the edges where the prior distributions were. And we can work out things. So these plots, the lines, the vertical lines that are on them, show 90% credible intervals. So in frequentist statistics, you might be quite used to having confidence intervals. We can have a similar kind of idea in Bayesian statistics based on these subjective probabilities, where we can have a credible interval that basically describes our belief that our parameter theta is somewhere in that interval. And you can get those for a beta distribution from R using the cumulative distribution function, but our credible intervals there for our Greenpeace activists, maybe it's in R. So we can work out the density of this beta distribution in R, and we can get those credible intervals there. So these two examples show how we can have really, really different posterior distributions based on what our prior is, but that as long as we get more and more data, our posterior is still going to converge together to look like the likelihood from our data. And so when we don't have an awful lot of data, knowing what somebody's prior distribution is becomes really important. But as we get more data, this becomes less so. So that was a case where we had really strong prior information from both parties. So what do we do when we don't have much information about theta and we want to convey weak knowledge? So you looked at sort of flat priors and things with Miguel. But how would we associate that with a binomial distribution? So how would we get a sort of, we said that our conjugate prior is beta, but how would we display this kind of weak knowledge? So we know that theta can only live on this scale between 0 and 1. So if we were to know nothing about theta, how can we represent that in terms of a distribution? So we might choose a uniform distribution, and then we have this equal probability across our whole range of what theta is. So then we just have our prior density equal to 1. And if you were to look, I think the information's in that like extra column at the end of your distribution sheet. A uniform distribution on 0.1 is the same as a beta distribution where A and B are both 1. So if that's the case, then we can still use, because beta is conjugate for theta in this binomial data case, we can use this prior that says that we don't know anything about what value theta can be. But because that's equal to a beta distribution, we can still use this whole conjugate information and all of the work that we've already done to work out what the posterior would be in that conjugate case. So we then know our posterior is still beta, and we can just plug in these values of A and B from what we did yesterday to get what this posterior would be. So if we were to look at moments from that, we're going to get that our posterior expectation is the number of successes plus 1 and our total number of trials plus 2. If we really were to have no information before we'd seen our data about what theta is that what we would expect to really have wanted to do with our posterior expectation? Really, if we didn't know anything about theta, we'd probably want our posterior expectation to just equal the maximum likelihood estimator of our data. So just the proportion of successes that we've observed. But in this case, we have these two values that take it away from that value. So even though this represents us knowing nothing about theta, and it's conjugate, so it's nice and easy to work out what our posterior is, it might not be particularly, although it's convenient, it might not be ideal because we don't have this quality that our posterior is only based on what we've seen in the data, because we have this extra bit that's added to it. Instead, we might want to look at transformations. So when Miguel was talking about weak priors, you looked at Jeffreys prior. So the point of Jeffreys prior is that any transformation that you do on your parameter, you still have this distribution that scales with that transformation. So if we were to actually want to look at some sort of transformation of theta, so if we had some new parameter that was theta squared, phi still lives on the same scale. So it's still going to be between 0 and 1. But if we were to set the same prior on this transformed variable so that it was uniform, because if we don't know anything about theta, so that that's uniform on 0, 1, then we don't know anything about theta squared either. It makes no difference that we squared it. So reasonably, we would want to set that equal to a uniform. But if we were to look at that transformation of this PDF, so in MAS6004, your first year stats module, you looked at transformations of PDFs. So if we were to do a transformation of this uniform PDF, assuming that phi is theta squared, then our PDF for theta equals that. So 2 theta. So you can work through that as an exercise. And that's not uniform on 0, 1. So now our transformation of theta, where we've squared theta, we're saying that we're ignorant about what value phi takes on 0 to 1 because we've given it this uniform PDF. But now when we take that back and just look at theta on its own, that's no longer uniform. So we have some sort of bias towards some values of theta, and we don't have complete ignorance anymore. So that's not an ideal situation to be in. So although this uniform prior gives us this nice conjugacy, it has a lot of downsides based on that. So instead, we could look at a different prior that had sort of no information about theta. So if we would say that theta was beta, this conjugate distribution, but where our parameters, A and B, are tending towards 0. So then that would give us a posterior. If we look back at how we get our posterior again, when we have this conjugate beta, we would get this beta distribution with just the number of successes and the number of failures. And that actually would give us then the posterior expectation that we were hoping that we would get if we didn't know anything about theta. So our posterior expectation then would be our maximum likelihood estimator, which is a really nice property to have because we don't know anything about theta, so we've let the data completely speak for itself, and what is most likely to inform us about theta is what we believe our expectation to be. But that distribution is not a distribution, because if we have this definition of what a PDF is, that if we integrate it over all values, theta can only lie on 0, 1, then that should equal 1. That's what all PDFs have to abide by. But if we look at that, where we have A and B equal to 0, you can try and solve what this is, but it's not equal to 1. And so our prior distribution isn't a proper distribution. So that would mean that our posterior distribution isn't proper. So it's not an actual distribution function. And so we can't use this as a full analysis where we say that this is our posterior, but we can say that it's an approximation to our posterior. So we can use that, and some people often do use improper prior distributions that are not PDFs as their prior, so that they can still represent ignorance about theta, their parameter, but they get the kind of posterior moments that they would expect to get with ignorance, instead of going with a conjugate prior that doesn't give you that expectation in your posterior. So in this case, you talked about Jeffrey's prior with Miguel. For theta, where we have our data binomially, Jeffrey's prior is actually proper and conjugate. So that's not always the case. You'll have exercises where Jeffrey's prior is not a PDF or it's not a conjugate distribution, but in this case it's both. And so if it's conjugate, then it's going to be a beta distribution, and it has parameters of A and B equal to 1/2. And if we were to look at our posterior expectation then of that, it's not going to be what we wanted from a prior distribution, because our posterior isn't going to be our maximum likelihood estimator. We're going to get this posterior expectation that has, instead of just our MLE, which was x over n, we have these extra values. So it's not ideal in that sense, but it does have that property that if we were to take any transformation of theta, then we would still get the same transformation in our prior, which is a nice property. This is one of your exercises to show that that Jeffrey's prior is that. So you can have fun doing that. And that's everything that we will be talking about on the beta distribution. So you have that exercise in your notes with talking about Jeffrey's prior. You also have some exercises to do with some grades, a teacher grading an exam. So you can do that. And there's some exercises in your problem booklet to do. But the other thing that we're going to talk about today is how we can extend this example to multinomial data. So multinomial distribution then is just a generalization of beta. So we've done the simpler example this week, and then this would be the more general example that maybe takes a little bit more algebra to get it looking how we want it to do. But multinomial distributions are basically, instead of a binomial distribution where you just had a 0 or a 1, a success or failure outcome, we now have k outcomes. So before So we now have this probability that our ith trial is equal to our jth outcome, given our parameter, and that's going to equal theta j. So in the binomial case, we would have had that the probability that xi was a success, given theta was theta, and the probability that it was a failure was 1 minus theta. So we have this condition that all of our parameters have to equal 1. So once we've already defined what theta is, we know what the probability of the failure is. So we're still going to have the same setup as before, where we have n trials. And now, in the binomial case, we would have said that we had n trials. We would have seen x successes. So if we say that x1 to x is equal to 1, and then all the rest of our successes, all the rest of our trials were failures, so they were 0. And so in our case, we have this vector now. Where we have the number of successes for each of our k outcomes. And we have our parameters that represent the probability of an outcome being each of one of those k. So we talked yesterday about how when we have n trials and we have this single x value of how many successes we have, we still have that in this case. We still just have one trial that are this one experiment of n trials. So we still just get one data point of all of these values, and you could have multiple repetitions of that, which is probably what one of your exercises is about extending. So you need to extend that to multiple, but today we'll just talk about if you have one. So the first thing that we do in any analysis is we need our likelihood. And in this case, we've said that it's multinomial. You can find that on your distribution sheet. And it's just equal to that. So you can see how the binomial PDF is just a special case of this more general PDF. And the prior for this, if we use a conjugate prior, we're just going to tell you that the conjugate prior for this is a Dirichlet distribution. I'm going to assume that you haven't seen this distribution before, so we'll talk about it for a little bit. Dirichlet is basically just another extension of a beta distribution in the same way as the multinomial distribution is a generalization of a binomial. A Dirichlet is a generalization of a beta. So it's not surprising then that that's our prior, because our beta was our prior in the binomial case. If theta, so this is our vector of thetas, remember, that's our probability of success of each of our 1 to k outcomes. And that's going to have this prior distribution where now we have this vector of parameters, one for each of our possible outcomes. So again, this is going to be on your distribution sheet to get the PDF of this. So we can write that down. And you can see, again, that this looks pretty similar to what we had with our beta distribution, but instead of just theta and 1 minus theta, we have k thetas. And we have what this beta function is just, again, a generalization of the beta distribution, the beta function that we had before, which is just this function of gamma functions. So your exercise then in the lecture notes, so this is 3.4.9, is to take this likelihood and this conjugate distribution and work out what the posterior is. So you have the PDFs for both of these. That's what we've got here. You know that it's a conjugate distribution, so you know what family of distributions your posterior is going to belong to, and you just have to do the work then to get what the parameters. So if our prior then we know that it's going to be Dirichlet, we just don't know what this is. So your task in 3.4.9 is to find out what that is. So the only thing to be aware of with this is that although this prior distribution of a Dirichlet is conjugate, so it makes things nice, our posterior is going to have this Dirichlet distribution and we can do that analysis. This might not be the best distribution to use as a prior. And that's because we have this constraint that the sum of our parameters has to equal 1. So if we're having this prior that has k components to it, this is our prior, it has k values, and we're trying to work out basically a prior for k minus 1, because once we have k of our thetas, the last theta is already defined because of this constraint on it. So if we were to use our alpha 1 to alpha k minus 1 to describe our expectations about each of our parameters that aren't then constrained, and we use that to describe our expectations of those, then we can do that. But then we only have one parameter left. We've only got ak left to describe all variances about all of our parameters. So we have just that one parameter to describe our prior variances of all of these parameters and also the covariances between them. And so it can be quite difficult then to get all of the information that we might have about our set of thetas into these k a prior parameters. So it might be convenient because it's conjugate, but it's not always ideal. And that's something to be really aware of, because if we don't use conjugate distributions, our analysis might become more difficult, and that will be what the sort of last chapter in your notes is all going to be about, how we can do that. So although we can do this convenient method where we know our posterior, it might not be useful for us to actually describe our prior beliefs. So that is everything on binomial and multinomial distributions. You have this exercise to be doing. And next week, we're going to move on to a different case study. So we're going to look at normal data, but whereas you did that where you knew what the variance was with Miguel, we're going to now do it where you don't know what the variance is. So you have the mean and the variance to estimate.